Hello, Professor Anna.
Morning. I hope you are okay.
Yes, I'm in the middle of something, so I just I just stay at home and try to see the situation. So, but uh, I'm not sure, but I'm okay. I'm fine. Uh, uh, I don't feel any kind of symptoms or etc. But I have to wait for maybe the next week for
Yes,
sure.
yes.
Mhm.
Well, it's
So,
good that at least you don't have any symptoms.
yeah.
But
So, Prof. Anna, do you mind if you start the
sharing.
presentation?
Okay. Can you see?
Yes, but maybe you have to.
Do it in presentation mode?
Yes.
Okay. So shall we start or?
Yes. Please,
Okay.
Professor Anna.
Okay.
Screen is yours.
Thank you very much. I would like to start by, well, saying good afternoon, good morning to wherever you are in the world, and thank this opportunity to share the work we've been doing with people from so far away, and especially having the opportunity to participate in this series of online seminar that an ex-student of mine, a very dear student, has been organizing and unfortunately couldn't do the talk at this time, but is acting as chair, which is an honor for me. So today I'll talk about organic inorganic hybrids with particular emphasis of polymers at interfaces. And those of you that may wonder where I am, well, I'm very near you in mind, but realistically, we are very, very far away. As you can see, we have to go around the globe to go from one point to the other. Specifically in Portugal, we are this little rectangular on the coast of the Atlantic Ocean. And Aveiro is a very small city that Aditya Tringona had the opportunity to visit and stay with us for a while. And within this small city, we have the University of Aveiro that is actually of a similar size of yours, around 15,000 students. And is also a reasonably young institution. It's roughly 45 years old. But we've been doing quite a bit. And if you would like to know a little bit more about us, you can visit us on this film on YouTube, which I would really appreciate if you do, even though I'm not going to load it now in case everything crashes, and we don't want that. So we work around this campus. My department is now, well, my office and labs are now in this building, which is an extension of the original building that Aditya visited or stayed with us. So we continue to slightly grow, not at the same pace as originally, but steadily we continue to progress. So As regards what we've been doing, I'll just start with a brief overview of of the research topics I've been working in the last years, but then I will focus on a specific topic. So when I said polymers at interfaces, I meant really in general. So we carry out work at the interface between research and industry in a very much top-down approach, as well as research at laboratory level, very much in a bottom-up approach. That's what I will be presenting today, is very much the bottom-up approach. Nevertheless, as you can imagine, we have to carry out a lot of work to get the funding as well as accommodate for the interests of a variety of students. So from the point of view of research in connection with industry, we have been doing work with more traditional companies in the field of polyurethane foams, as well as adhesives, especially urea formaldehyde adhesives. Even though these are very traditional industries, there is still plenty of work to be done to fully understand the parameters that influence the quality of the product, as well as the savings that are more and more necessary in terms of resources, and also to minimize pollution and environmental impact. So there is still plenty of scope within the traditional manufacturing aspects to work and to carry out research. Also, we need to, like everybody else, to look into the circular economy approach to manufacturing and to explore as much as possible the the value that a lot of side products have. And this is a case of the paper companies that produce lots of lignin, which normally are burned, are used for production of electricity. But actually, lignin is a very rich chemical, and we can use it to do a lot of other things with much higher added value. And in that sense, we have a couple of students. Well, I have, but there are other students also working in this larger project with the paper companies. But the students that are working with me are trying to develop functional foams, concrete plasticizers, adhesives, as well as conductive polymers and functional foams. Also, we have a lot of work funded by companies and the EU and governmental funds to carry out the recycling of polyurethane foams, which, as I have here, it's an abbreviation, PUFS. Moving on to the research at laboratory level, we have been doing quite a lot of work for a long time with polymers at nanoparticles. I will be talking today about gold nanoparticles modified or coated within polymeric materials using living radical polymerization, or more correctly, reversed deactivation radical polymerization. We followed different approaches, which I will discuss later. Also, we have projects going on, but on polymers from renewable resources, functional blends, and composites. One of the most important ones are based on polylactic acid grafted at the graphene oxide to prepare sort of hybrids, which are then dispersed in commercially available polylactic acid. This leads to the possibility of growing chains or grafting chains of PLA on the surface of graphene oxide with different sizes, and then disperse them in a matrix with the commercial PLLA. As a result of that, we have different mechanical properties and different electrical performance as well. But today I just chose to focus on one topic, so I'll leave this to a future opportunity if it comes with you or with some other situation. We also in the related to these polymers from renewable resources, we have work going on blends of PLLA and ionic liquids for fuel cells, and also silk fibrine, which is a material coming from the silkworm that is also showing quite interesting performance as electrolyte for fuel cells. Other activities related to polymers from renewable resources also include the use of gelatin or even starch to blend with PCMs, so phase change materials, as well as EG, which is expanded graphite, for the purpose of energy storage, mainly to use in refrigeration systems. But this work is still at a very early stage, is proving rather challenged. So unfortunately, I don't really have many data to share with you on that one. And so that was definitely out of question to discuss or to present today. But anyway, so as I said, I chose to tell you more about these organic and inorganic hybrids based on gold nanoparticles and synthetic polymers using controlled radical polymerization. So the aim of this work, I will first present, then I'll make a brief introduction about gold nanoparticles and surface modification and functionalization of gold nanoparticles. Next, I'll move on to surface modification and functionalization strategies that we have explored. Then we try to immobilize these gold nanostructures in thin films. So I'll show you some results. I'll then, of course, finish with some conclusions and the perspectives for future work. So as regards the aim of the work, the idea was to develop strategies to prepare gold nanostructures for biosensing applications. So schematically, we have here the polymer at gold nanoparticles, so a shell of polymer around a gold core. The objective was to carry out a biofunctionalization by incorporating in this shell biotin, so the bioreceptor, and the fluorophore. And the idea was when in the presence of avidin, the analyte, we would get optical biosensing response And the technique to use would be essentially optical measurements, either visible spectroscopy and or fluorescence spectroscopy. So how to go about this? Well, first of all, we have to remember that we chose to use gold nanoparticles because they have received a lot of interest. And why do they have all this interest? Because they have this localized surface plasmon resonance. This plasmon resonance results from the interaction between the electromagnetic radiation and the gold nanoparticles. This actually is the result of the collective oscillation of conduction electrons forming a dipole, and this can then be used for, excuse me, can be used to take advantage in terms of biosensors. Now, as you well know, the gold nanoparticles can vary a lot. It can be, we can have nanospheres, we can have nanorods. Also, they can have different sizes depending on the reaction conditions we choose. We can tune all of these. And finally, depending on the medium they are in, they will have different wavelengths at which they absorb. So it depends in terms of surrounding medium. It depends on the refractive index, the aggregation state resulting from that, as well as the presence of complementary targets that lead to the aggregation or not, and therefore to a shift of the plasmon signal. So another aspect is that we can functionalize these nanoparticles with fluorescence quenchers, and depending on the distance that this fluorophore is from the core, we'll have different signals. For example, if the distance is very short, we have lower intensity of the fluorescence, so we have high quenching effect. If it is further away from the core, the fluorescence intensity is higher, and we have therefore less quenching effect. And this has been explored by others in biosensing. So you have an example here from 2006, and after that, many other examples have been reported where the signal, the fluorescent signal, has been used to detect the presence of biotin and using biotin-related gold nanoparticles. So with this in mind, we then moved on to attempt the preparation of gold nanoparticles for biosensing, biosensing applications. But for this, you need stable nanoparticles in physiological medium. Therefore, we need to carry out surface modification and functionalization. This can be done by a variety of methods. Amongst the two, the many methods available, two are particularly well known. One is via layer by layer method, and the other ones is encapsulation of the nanoparticles with polymers. Specifically, within this second strategy, we can use living radical polymerization, and it's exactly what we did, exploring raft polymerization. So just as we also carried out layer by layer method, but I'm not going to elaborate on this today. So in the layer by layer method, we basically have the gold nanoparticle, and then we alternate the deposition of a polycation, wash, get the charges on the surface changed from negative to positive. And then we immerse these nanoparticles or add these nanoparticles to a polyanion, wash, and again have now the surface charge is changed. So we can repeat these a few times and increase the size of the shell. This was actually done with some polycations and polyanions, and it was actually reported. But as I said, the idea in this talk is to tell you more about different strategies to functionalize and modify the nanoparticles using Raft polymerization. So Raft is a reversible addition fragmentation chain transfer polymerization. The greatest advantage of this strategy or this polymerization mechanism is that it allows us to prepare tailor-made polymers, and in that sense we can control the molecular weight, so obtain narrow molecular weight distributions. We can control the composition and architecture of the polymer. Also, we can use mild reaction conditions, and we can use several types of monomers, including monomers with functional groups such as hydroxyl groups, carboxylic acid groups, amides, many different types of functional groups, because it's a very tolerant type of polymerization mechanism. For that, we use a chain transfer agent called CTA or Raft agent. As you probably know, basically is a dithioester, sometimes also can be a trithioester. It varies, but at least we have a dithioester where we have a leaving group which has a very weak link with the sulfur group, and is the one that will be broken and expelled so that the reaction can continue. And also has this Z group that modifies the addition and fragmentation rates during the polymerization. We start with a radical species, which comes from a typical polymerization initiator, and then we will establish a series of reactions that will allow this polymerization to be carried out in a controlled way. So in a more larger overview, I'm showing here we have a standard initiation process, which involves an initiator breaking down into two radical species, the initiation step involving this initiator reacting with monomer and starting a growing chain. Then finally, we start the interaction with the Raft agent. So we have this reversible chain transfer at a sort of pre-equilibrium, where the growing chain is going to transfer its growth to the chain transfer agent, reaches or forms this intermediate radical, and then the R group is kicked out. This R group will start another growing chain, and this new growing chain will then interchange with the previously formed Raft-Intermediate or chain transfer agent. And this goes on so that the chains are in a dormant state and don't actually terminate. And in that sense, we managed to both control the molecular weight by using adequate ratios of Raft transfer agent and monomer, as well as concentrations of initiator well established. And we can, because it doesn't, the chains don't actually terminate, they are just in a dormant state, we can add different monomers and therefore form block copolymers with the sequence that we desire, because it all depends on the ratio of monomer and Raft agent that is used. So using Raft, we can then prepare gold-based nanostructures following a variety of strategies. We can use in situ preparation, we can use post-modification, which is also referred to as grafting too. We can prepare these nanostructures, hybrid nanostructures, using the grafting from and also the grafting through. Now, these may sound all a bit strange or may sound all the same, but it's not exactly the same. And in fact, we assessed this variety of strategies, and in the end chose, I can tell you in advance, the grafting from strategy. But of course, this is sort of obvious when you have tested and know the final results. So we focused on spheric gold nanoparticles, so nanospheres, but we could have used surfaces or even gold nanotubes, nanorods in particular. I can tell you in advance that we carried out the works with nanorods, not exactly gold ones. We used, as it was in the first slide, gadolinium oxide doped with europium and coated with silica to encapsulate these nanorods. And once we have anisotropic structures, this strategy can be far more complicated. So we decided to use gold nanospheres because life is much easier in that sense. So with that, we looked into the literature and tried to see what had been done and what parameters would influence the generation of these gold nanoparticles. So in this approach, we were looking at the preparation in situ of the gold nanoparticles after preparing our own polymer. So we looked into the literature, as I said, and saw that others had already looked into that, but using different polymers, namely Destarac had reported a very detailed amount of work using a very distinct type of polymer, but realized that as the concentration varied, the size of the particles would definitely be an issue. So increasing the polymer concentration, the size of the particle decreased, and of course the optical properties would be distinct. The other approach that we had looked into was the grafting from. In this case, we have two steps. First, we have to anchor the raft agent onto the nanoparticle surface, and then the second step involves the polymerization from the nanoparticle surface. Again, we had seen in the literature that people had looked into this. So prepare the nanoparticles, and then promoted the anchoring of the chain transfer agent or the raft agent onto the surface of the nanoparticles, and from there grew the polymer chains. In this case, this was a sort of conventional approach in the sense that it used organic solvents and standard radical polymerization technique. So IEBN and DMF and 60 Celsius. So it was obviously an important contribution, but still there wasn't much control over the characteristics of the polymer that was being anchored. So that's why we looked into what had been done before or in the meantime by Ockett regarding raft-mediated emulsion polymerization, which later on was coined as REAP. And these guys used emulsion polymerization combined with raft to coat particles. In their case, they coated pigment particles, and they managed to encapsulate them very neatly without having free polymer, or at least not much free polymer around. And this was exactly what we wanted. So we looked further, and in the meantime, other works had been also reported using this combination of raft polymerization with emulsion polymerization. Of course, this requires very fine tune of the size of the blocks of polymers that we use. So it's not as straightforward as it may sound, but the heart of the matter is it allows this neat encapsulation of nanoparticles. So with this, we decided to then consider a full evaluation of how to go about what we wanted. So we, as I said, focused on this second approach, the grafting from approach. But we first started by preparing the micro raft agent, which from now onwards will be designated as MR, carried out the co-polymerization and emulsion polymerization, and then added the gold nanoparticles, and we call this as a post-modification strategy. Also, this copolymer prepared by a raft in emulsion was also used for this in situ preparation of the gold nanoparticles by adding the gold precursor followed by the reduction and formation of the gold nanoparticles. As an alternative, we also looked into the grafting from strategy, but again, in this case, we considered two approaches. One, the generation of the gold nanoparticles in the presence of the micro raft, and two, the absorption of the micro raft onto the gold nanoparticles, followed by emulsion polymerization. Basically, the chain extension was carried out in emulsion conditions. As regards the macro raft, we started by the preparation or the synthesis of the macro raft using basically a raft agent that is commercially available, designated here as TTCA, where the Z group is a C12H25 S, and the R group contains a carboxylic acid, which can be useful for further modification. The polymer that we grew was based on ethylene glycol methyl ether acrylate. So we used also this initiator ACPA, and the reaction medium was in ethanol, all this to prepare the macro raft agent based on what we call PEGA, so this polyethylene glycol methyl ether acrylate, because it is well-known type of polymer for use in biological tests, and also has some responsiveness to temperature, which can be further explored if one wants. From the macro raft, we also prepared this block copolymer, now in emulsion polymerization, again using ACPA, but now adding the methyl methacrylate and butyl acrylate as hydrophobic monomers to yield this copolymer that as it contains an hydrophobic part and a hydrophilic part, can self-assemble and actually make nanoparticles, so small structures with sizes in around 100 nanometers. One very short polydispersity. These particles were the ones that were then used to prepare the hybrids, either using post modification strategy or by preparing the gold nanoparticles in situ. As you can see in the images, the results weren't exactly as good as one would want, especially because we would have these patches of polymer without any particles, or we would have aggregation of the particles. So it proved that we needed to do more work. As regards the formation of the gold nanoparticles in the presence of the macro raft agent, we had to, first of all, assess the influence of the parameters that determine the type and the quality of the gold nanoparticles prepared. First of all, one aspect was the effect of the pH. Also, the ratio between the gold precursor and the concentration of the macro raft, as well as the time, as I'll show in a few minutes. So we realized that, in fact, the ratio of the gold precursor to the macro raft had a major impact. Also, the working at pH 7 or at pH 3, for example, caused a significant change in the size of the particles that were obtained, and of course, in the aggregation level. Also, the time had a major impact. So these are all too many parameters to try to control if we want to make some sort of biosensor. This is not really terribly practical. That's when we definitely moved to the grafting from approach strategy or chain extension. This involves like two steps. The first step where we prepare the micro raft adsorbed onto the gold nanoparticles, and the second step when the growth of the hydrophobic chain takes place. The preparation in the first step, we have the preparation of these micro rafts chains adsorbed at the gold nanoparticles. So it involves the generation of gold nanoparticles in the presence of the micro raft agent, and the other one involves the adsorption of the micro raft agent on pre-prepared gold nanoparticles. This is all okay, but we have to bear in mind that the macro raft himself has amphiphilic characteristics. So working above or below the critical micelle concentration is a major issue. The problem is how to determine the critical micelle concentration of polymeric material that is not really charged. So we looked into different techniques. Of course, the conductivity wasn't very useful because the micro raft only has a carboxylic acid group at its end. We also considered measuring the size, so using DLS and zeta potential. As you can see, the identification of this critical micelle concentration isn't straightforward under these conditions, but it allows us to identify the concentration range at which the micelles are formed, above which they are formed and below which we do not have these micelles. So based on that, we actually looked into what happens when we carry out the absorption of micro raft agent onto the nanoparticles above CMC. And we could see that, okay, it sounded fine, that the particles, especially after encapsulation, had increased their size, but the polydispersity for encapsulated particles looked okay. The problem was that above CMC, we do not obtain only this, which sounds very good, but we also obtain other morphologies, namely fibers could be detected that were not necessarily encapsulating the nanoparticles. So in view of this, we had to study the results using the micro raft agent below the critical micelle concentration. And in that case, yes, we have, well, encapsulated particles that are individually encapsulated, as you can see, both just when they were coated with the micro raft agent and after carrying out chain extension with the hydrophobic monomers to form this hydrophobic shell. So working below CMC was the solution. Now, in terms of what happens to this micro raft agent first during the first stage, which is the adsorption, we believe that there are interactions during this adsorption step that involved the coordination between the sulfur groups onto the gold surface, as well as interactions of the Pega chain with the gold surface. When chain extension takes place, so when these microraft particles combined with are anchored to the gold nanoparticles are dispersed in water, so that we proceed with the chain extension. What happens is the new chains that are formed in the medium will try to also adsorb at the surface of the gold nanoparticles. So this will force the chains to point outwards and in order to accommodate as many as possible chains on the surface of the gold nanoparticle. So this may be improved further, but for the moment, the amount of polymer anchored on the surface of the nanoparticles proved to be sufficient to change the properties of the gold nanoparticles. And having succeeded in encapsulating the gold nanoparticles, now we have to move to what we actually wanted, which was to do this, but for a purpose. The purpose was biosensing. So the next stage was to carry out the functionalization of these nanoparticles. So to do that, we had to anchor the biosensor bit, which in this case was biotin. So starting with the copolymer at the surface of the gold nanoparticles, we added actually a few repeating units that could react with the biotin to prepare biotinylated copolymer gold nanoparticles for the biosensing tests. So to do that, as I said, we had to adjust a little bit the composition of our macro-raft agent. So besides the Pega, we had to add a few, very small number actually, of acrylic acid, which was then functionalized with 3-azidopropanol, and this requires monitorization, of course, to double check that the azide group was anchored onto the nanoparticles, or onto the polymer, in fact, and then proceed with the functionalization with the biotin. So this, once we added this azide group, we had to be very careful and adapt to the polymerization conditions. So we actually had to change initiator and work at much lower temperature because, as you know, azides are groups that are very dangerous and can lead to explosion reactions. So we had to study all the conditions again to adapt to this new initiator. But anyway, it just slowed down to a certain extent the reaction, the polymerization reaction, but allowed the preparation of these functionalized gold nanoparticles with this azide group, which later, via click chemistry, allowed the anchoring of biotin to the gold nanoparticles. These gold nanoparticles were biotinylated, were compared with the conventional, well, the original gold nanoparticles functionalized just with the copolymer. In the presence of avidin. For control, we used another protein, BSA, and also as a control or a blank, we used physiological serum, so that we knew that whatever result we were going to get was associated exclusively with the analyte, in this case, avidin. So as you can see, this functionalization strategy worked, because whilst in the presence of the copolymer gold nanoparticles, avidin didn't really cause any major shift of the surface plasmon absorbance, and it was essentially equivalent to what could be seen in the presence of BSA, the control protein. These are due to the medium changes, but not really molecular recognition at all. Instead, in the presence of biotinylated copolymer particles, gold nanoparticles, when in the presence of avidin, the response was pretty clear. And as you can see, the particles aggregated, therefore, it means that the nanoparticles have interacted specifically with avidin. So we had the confirmation that this strategy was okay, but still we wanted to assess how this polymer or polymer shell was actually interacting with the analyte avidin. So we carried out a parallel study, in this case using the Langmuir monolayers of copolymer, because we couldn't use the nanoparticles, as they would just disperse in water. They are aqueous colloids, so we couldn't really use the golden colloids. So we just used the copolymer spread at the water surface in a trough, as you can see in the bottom corner, and exposed this monolayer that forms at the air-water interface and can be organized by compressing the barrier, so reducing the area available to this monolayer by compressing it. So we can go through different organization levels. So when the barriers are completely open, we have the so-called gaseous phase. As you compress the monolayer, it goes into a liquid expanded phase. And finally, when the area available is minimal, you have a so-called liquid condensed phase. So in that stage, we can inject the analyte, in this case avidin, into the subphase and see what the result is. And in fact, well, this is just to show you the monolayers were stable, so we could expand, close the barriers and open, and the result was okay. So the monolayer was stable. So we moved on to this test of testing the copolymer at the air-water interface, the copolymer with biotin at the air-water interface, and finally the copolymer with biotin and after injecting avidin in the subphase? Well, it seems that there is nothing happening, it seems. However, this time was very short. The time of contact was very short. So we decided to assess this in using longer times. And it proved that actually the interaction between the bioanalyte and the bioreceptor, so between biotin and avidin, is time dependent. And if we allow more time of contact between the monolayer and the avidin in the subphase, in fact, the isotherm that we observe is pretty different after 1 hour. So the tests we had done originally using 15 minutes were really very short to get any conclusion. But if we allow at least 1 hour, we can see that really avidin tends to interact with the biotin as expected. So, having managed to functionalize these gold nanoparticles with a bioanalyte, we wanted to move on and also anchor a fluorophore, so that besides the studies that we carried out using optical microscopy, optical spectroscopy, we would like to use fluorescence. So we try to take advantage of this possibility of Raft polymerization to co-polymerize the macro Raft agent with another monomer which had been modified with FITC, which is a well-known fluorophore. So for that, we had to react this macro Raft agent, which was already anchored or absorbed at the gold nanoparticles, and graft this other monomer that had been functionalized. And the idea was to later carry out the chain extension using the same type of monomers that were used in the previous strategies. We did that. We monitored the response of these materials via optical spectroscopy in the visible region and also via fluorescent spectroscopy. And clearly, the results after chain extension, described here as CE, lead to significant changes as one would want. So as we anchored the macro Raft onto the gold nanoparticles, we have a change, small change, so from 520 to 522.5 nanometers in the absorbance maximum. But once we anchored this fluorophore, and so carried out a chain extension of the macro Raft, this change, this shift of the plasma resonance maximum really changed to 527. In terms of fluorescence at excitation of 495 nanometers, the effect was really quite astronomical once we tested the chain extended particles. So the presence of the fluorophore really led to these significant different results. However, I must say that none of this still has the biotin, so could not really be tested for the bioassays. So we just succeeded in preparing this copolymer containing the fluorophore and anchoring it or encapsulating the gold nanoparticles with this functionalized copolymer. But the idea was to combine this fluorophore with the biotin and use all of that as biosensing materials. But the results weren't as straightforward as one would expect because of the reaction conditions involved, namely the polymerization. But that we can discuss later. Finally, having prepared these gold nanoparticles, but they are in the colloidal form. So to use them as a biosensor, ideally one should try to immobilize them so that the use of the biosensor is more practical. So we try that using the layer by layer deposition and study that. So using a substrate, in this case was actually glass. So we deposited different layers of polyanion and polycation, and at the top we deposited the suspension or the colloid actually of our functionalized gold nanoparticles. So to achieve that, which is a well-known technique, the layer by layer deposition, we still had to carry out some studies, namely assess the effect of the molecular weight of the polyelectrolytes, the effect of pH and ionic strengths, washing and drying steps, namely the time between them and so on, the deposition time, the number of bilayers, and so on. So as polycation, we use the PAH, which is very well known, and as polyanion, which wasn't really an anion, we used for the intermediate layers just our copolymer, which had, as I mentioned earlier, carboxylic acid at the end, so acted as enough charge to allow the interaction with the following layer of the polycation, the PAH. So we did this, and then at the last step, we deposited the colloid with the gold nanoparticles. And we monitor that to assess the evolution of the number of bilayers with the absorbance under different conditions, namely time. And clearly 10 minutes seems to be a good compromise to get this preparation of thin films to immobilize these functionalized gold nanoparticles. So, as a few conclusions of this work, we can realize that post-modification and in situ strategies are actually very straightforward techniques or strategies, but do not allow to prepare shell at core type nanostructures. As I showed you at that time in the early slides, we had just aggregates of particles and then patches of polymer, so not really well controlled shell at core nanostructures. Nevertheless, the nanocomposites, if you can call them, because they are a mixture of two phases anyway, presented the optical properties of the gold nanoparticles, so they may be used for other applications. Grafting from followed by chain extension strategy led to core edge shell type nanostructures using two steps. So first, the macro raft at the gold nanoparticles are prepared via generation of gold nanoparticles in the presence of the macro raft. But in this approach, the synthesis depends on a lot of parameters, namely the pH and the ratio of the gold precursor and the macro raft, as well as the time. So it's a bit demanding. Another approach which proved to be quite robust is the preparation of stable copolymer gold nanostructures obtained by adsorbing the macro raft onto the nanoparticle surface and following it by chain extension using an hydrophobic combination of monomers and RIP or emulsion polymerization, actually. The biotinylated polymer anchored at gold nanoparticles were then successfully prepared. The macro raft agent was prepared using this azide, and 44 degrees Celsius was required for the use of the VA044 initiator. Alkylated biotin was covalently bonded via click chemistry to the nanostructures. Gold copolymer nanostructures labeled with biotin responded specifically to biotin. Langmuir monolayers of the copolymer allow to study the interaction of the copolymer biotin avidin. But of course, if we wanted to really know the kinetics, further studies would be required. As regards the fluorescence copolymer gold nanoparticles prepared via Raft, the FITC labeled monomer from the macro Raft was obtained, but this procedure still needs optimization, especially if we want to combine the fluorophore, the anchoring of the fluorophore with the biosensor. So as regards the preparation of or more robust structures, specifically the immobilization of these gold nanostructures onto thin films. The use of LBL proved to be rather efficient to achieve that. And strategies to biofunctionalize azide copolymer gold nanoparticles via click chemistry really should be optimized and explored for using with other molecules or bioreceptors. I mean, the studies with combinations of antibody and antigen are really a possibility. Chain extension using RIP strategy is then shown to be a very promising approach to many other applications, namely for drug delivery, using molecules that have low solubility in water, and also this use of PEGA allows to explore the thermal responsiveness of these nanostructures. coating of other nanoparticles, namely gold nanorods or silver nanospheres, and so on, may allow the exploitation of these functional nanoparticles for surface enhanced Raman scattering, which can really be quite promising. So in brief, I told you a story here that can be summarized by these pictures. So in one hand, the coating of or the encapsulation of gold nanoparticles with by a raft in emulsion, and the functionalization of these gold nanoparticles and their testing in the presence of a analyte, in this case, avidin. This work was very much carried out by Sonia Pereira, who is now Dr. Sonia Pereira. So this was very much part of her PhD work. And my colleague and friend, Professor Tito Trindade, who was Sonia's co-supervisor and whom I very much thank for this long-term collaboration. Also, I have to acknowledge the funding that this project received from our funding agency. And above all, thank you for your attention. And I hope I can see you again in Aveiro sometime. And now I am open to answer any questions if I'm capable, of course.
So, thank you for the presentation, Professor Anna. So please, for the participant, just unmute your microphone if you want to ask a question to Professor Anna. So maybe I have a question to you, Professor Anna.
Yes.
Till we wait the question from the participants. So it's about the surface modification or the functionalization. Maybe can you explain more about why this surface modification or functionalization is so important in these topics?
Yes, that's a very important question. I mean, gold nanoparticles are very interesting, but on their own, you cannot do much. So you have to a certain extent, functionalize them with, for example, in this case was the biotin, so that you have a biosensor. So you have to develop strategies to functionalize these nanoparticles so that you can take advantage of their surface plasmon properties. So to act as a sensor, be it a biosensor or any other thing, they need to be functionalized. On the other hand, they have to be robust, and they should not aggregate. Otherwise, their the signal is no longer so the surface plasmon resonance is no longer so useful because the particles aggregate. So you have to get them well dispersed in other words, form a gold colloid, and that's why the encapsulation is important. So you asked about surface modification and functionalization. So surface modification may just mean modify the surface to prevent aggregation. But functionalization is one step forward, is to actually add some functionality to the nanoparticle. In this particular case, the functionality was for biosensing. So a biosensor bioreceptor was anchored onto the gold nanoparticles. To further explore that, we were considering to anchor also the fluorophore, but in this case was to get the signal of detected by photoluminescence and not just the optical properties. Simply because if we go for the photoluminescence, we need much smaller quantities because it's much more sensitive.
Okay. And maybe can you tell us about the commercialization of this method? You mean with the Raft, with the Control Radical Polymerization, to
Yeah.
optimize the use of this nanoparticle? Is there any commercial product in the market so
Mm.
far? Or?
Yes, you are again very right. I mean, these are essentially academic studies. There is a potential for this, especially under these present conditions with the pandemic. You could well imagine that these type of sensors are pretty easily adapted to detect coronavirus. The question is the price. Of course, um, it's not so straightforward. It just opens ways of testing strategies and characterization strategy of techniques, also strategies to understand the interactions between the bioanalyte and the bioreceptor, as in the case of the Langmuir-Blodgett studies, allows developing techniques to immobilize them, to make more portable sensors, such as the LBL studies, seen films that were prepared. But realistically, if you want to go from here and start, a startup company to start commercializing, I wouldn't think this would be very realistic. You would have to make use of the knowledge acquired and now simplify it so that you can get a commercial product. Because really, combining raft click chemistry, emulsion polymerization, all these may be far too expensive to go into the market unless there is really a very specific niche. But it does show us, allows us to understand how things work, and then you can go from here to develop a more simple process to prepare these biosensors.
Thank you, Prof. Anna. So, is there any question from the participant, please?
This topic may be very specific, especially for the background of people attending. But if they want to go back to the first type of slide, as I mentioned, we carry out work at different interfaces, so with industry or with other approaches like the circular approach. So by all means, you can if you want, I can go back to that, including the polylactide composites. Feel free to diverge if you want.
Yes, yeah, because for example, in my department, the topic about this, for example, control radical polymerization or functionalization, surface modification. I think we don't teach our students so much about this topic because it's advanced. Maybe here it's advanced knowledge. So
Yeah, I guess so. That was on purpose to open the discussion for other fields. So you were going to talk about what you call
functional material.
yeah, from renewable resources or so functional materials for sustainable development. And I, based on that, so okay, I'll go and talk about something else. But ultimately, this type of approaches, as I said, it's very fundamental studies, but that aim at the development of more sustainable materials. The thing is, to achieve that, you can't go by try and error. You have to look into the fundamental things, how to control, for example, the distance between the fluorophore and the core in order to get a response. How to the effect of, like in the case of the work that I just mentioned in the beginning that we are doing using graphene oxide with PLA chains grafted on the surface. Again, from a practical point of view, that is not really very feasible, but it allows us to understand the importance of the interface and how, in fact, I have to admit that that topic was, and that idea is still a reminiscence of your own idea when you were here working with carbon nanotubes and using ATRP to grow chains from the surface of the nanotubes. So you probably don't even imagine that we are still indirectly, okay, no longer with carbon nanotubes, no longer with ATRP, but still assessing how the load transfer can be affected as a result of the interface that exists between the filler and the matrix.
Okay, so maybe this is the last question, Professor Anna. So maybe the participant will get the knowledge why what is the difference between conventional polymerization and this control radical polymerization, because it's maybe in Indonesia maybe it's not really maybe the students they don't really know what is a control radical polymerization. So maybe you can explain a little bit the difference between conventional and control radical polymerization.
Okay, that's really a very fundamental question and important. When you are not familiar with that, then it can get really very compensated. So when we talk about a conventional, so to speak, radical polymerization, we have an initiator that breaks down into two radicals. These radicals react with the monomer, and you have the propagation, which is very fast. And these growing chains have a radical species, which is extremely reactive, and this reactivity is a result of the fact that we have unpaired electron in that reactive center. So we have the initiation, we have the propagation, and automatically we have the termination, i.e., two growing chains meet and react instantaneously and terminate. So in this sense, you form a polymer chain in less than 1 second, okay? So with this speed, it is basically impossible to control the molecular weight. So you'll have in the product um, polymer chains with very different molecular weights or with very different chain lengths. So the properties of this polymeric material are not going to be the same as they would if you have all the chains with the same size. Moreover, you can form uh, copolymers using conventional radical polymerization using two different monomers. But you will not have any control on how these monomers, different types of monomers, are distributed along the polymer chain. Because, as I said, the radical species are so reactive that they will just react randomly. Of course, depending on the nature of these monomers, you may have sequences of one type of monomer or another, but not control. As opposed to that, people have worked and developed strategies. This was in the 90s and in different parts of the globe, including some neighbors of yours in Australia, started this raft polymerization. Others uh, in America started ATRP. Others used another version of it, which is NMP. So all of these are so-called controlled radical polymerization approaches, which promote the transference of the growing species or the radical species to chain transfer agent, and in this way the the termination step doesn't really occur. What happens is you transfer the growth of this chain into this chain transfer agent. So the chain is in a dormant state, not dead. Therefore, you can control the molecular weight and so form uh, chains all with the same size. And you can prepare polymers with well established composition because you can feed this first monomer and then consume. Then when it's consumed, totally consumed, you add another monomer, so you can form block copolymers. Um, as a result of this fine-tuned composition and chain lengths, you are in a position now to form very different structures. So as you know, polymers can self-assemble, especially if they are amphiphilic. In other words, if they have a component that is hydrophobic and another that is hydrophilic. So they can self-assemble. And depending on the size and composition of the copolymer, we can have normal standard spherical structures. We can have more um, rod-like structures. You can have varieties of structures such as lamella structures and so on. And these can then be used as templates to form, for example, hybrid materials, for example, or to accommodate inside them um, drugs for later to carry out drug delivery and things like that.
Okay. So I hope the participant uh, which have a different background will understand what is the difference between conventional polymerization and this control radical polymerization, because it is the basic concept of the topic of Professor Anat today. So I will ask once more, do we have any question from the participants? Prof. Anna, do you mind if you send the PowerPoint to me by email so the participant will get your presentation?
Yes, of course, it is a pleasure. If it is too heavy to go by email, I'll send it via file transfer or something. I'll share that with you.
Mhm.
And I strongly
Yeah.
encourage the participants, which I fully understand that if you are not familiar with this field of science, that it may have been difficult to follow, but by all means, feel free to contact me at some other stage. I'll add my email to the front page, so
Mhm.
you can always try to email me, and then we can talk via Zoom um,
Yes.
to clarify some ideas, just to open your background to other fields, and it would be a pleasure, of course, to share that with you.
Mhm.
And I
Uh,
thank you for your patience because considering it's not your background, then this must have been really very hard for you. And I appreciate the effort you've made.
yeah. Yeah. So one of the aim of this seminar online is to introduce or to develop the awareness of the participant, especially in Indonesia and in my department, about many topics in metallurgy and material science and engineering. So that's okay, Prof. Anna, because it will help the participants and also other people to aware about the development of the many science and technology development in material science, for example.
Okay, thank you very much. And nice to share this session with you. And I hope you feel
Mhm.
okay and continue to feel well.
Yes, thank you very much. And you too, you stay safe and health for you and for your family, Pravana.
Thank you. Thank you. We will.
Thank you very much. Bye, Pravana. So for the participants, please complete the Google form for the present of this online seminar. And then in a few days, we will send you the e-certificate and the PowerPoint from Professor Anna to you by email. So I will give you around 10 minutes to complete the Google form, and then I will stop this Zoom meeting. Thank you very much to all of you, especially Prof. Anna. Stay healthy and please be aware with this COVID-19 pandemic, because here I'm in my office, I'm at home, and because there is something happened with my colleague in the university, so I have to isolate myself until, I don't know, maybe 1 or 2 weeks. So thank you very much, and maybe see you in the future. Bye, Prof. Anna. Bye, all the participants. Thank you.